Okay, good afternoon everyone. Welcome to the 7th lecture of 224W. So today we're going to be talking about graph representation learning, and as promised from last week, we're going to start to cover the most recent topics in machine learning related to graphs. So if you've been following the evolution of deep learning, you know that the field of representation learning is producing a lot of exciting work, and what we're going to try to do today is to give an overview of how representation learning can be applied to graphs. So if you recall, this is the same opening slide that we had on Thursday. One very classic problem that you can have on graphs is node classification. So on the left, we have this semi-labeled graph. You know, we have the label for a few of these nodes. Some of them are red, some of them are green. And for the gray one, we have a node label. So what we want to do is apply our classifier and then being able to give a label to each one of the nodes that were previously unlabeled. Okay? So this is the task on node classification. And we went in depth on this on Thursday, but it's definitely not the only task that one can work on with a graph. Another example, for instance, is link prediction. So we're given this graph where some of the edges are missing, okay? But we know for a fact that there should be a relation instead between these two nodes. So what we want from our machine learning algorithm is the fact that it will be able to tell us with high accuracy the fact that this edge should appear between these two nodes, while, for instance, these two nodes are not a good candidate to be neighbors, all right? So this is another example of task. And if you came to my office hours regarding the projects, we might have already talked about all the different things that you can be doing on graphs. So the idea is that with this week and the next one, we're going to be able to give you a tool set of the different things, the different predictive tasks you can have on graphs based on the latest machine learning techniques. Okay? So let's start from a high-level life cycle and basically try to explain why representation learning is so powerful, and it makes your life also much easier when you're working with graphs. So ideally what we usually do in supervised machine learning is that we always start possibly with the most boring part of the pipeline, which is we're given the raw data, we spend a lot of time cleaning this, making sure that it doesn't contain duplicates, errors, and so forth. And then what we want to do is we try to turn it into some kind of structured data that will be a viable input for our machine learning pipeline. And once we obtain this data, then we feed it into our learning algorithm, and hopefully we obtain a good model that fits our needs. And this part here, even if it's just represented as one edge, in reality, most of the times it has been said that it takes up to 70–80% of your effort in terms of development. And this step is called feature engineering. Okay, so you go from raw data to a structured data that is a viable input for your learning algorithm. And this is well known to be, first of all, painful, requires a lot of effort, and also it's very prone for you to forget what could be good features, okay? So you might be missing some key aspects of the data just because you didn't think of adding yet an additional feature in your feature set. So, and once we're able to do all of this, then we're going to be able to work on our downstream task. So once we obtain our structured data, then we can try to think about different predictive tasks. Now, what we will want in reality, what will make our life much easier is to get rid of the feature engineering, okay? So we want basically to automatically learn the features. And this is possibly one of the two main promises coming from deep learning. It's not only the fact that now we have very powerful and deep classifiers that are able to capture a lot of inductive bias from our data, but it's also the fact that we are slowly moving away from the classical machine learning point of view, where we work on doing feature engineering, to then the recent techniques where we hope that our model is able to automatically learn the features. Okay, so I hope I convinced you why we want to do this with graphs as well. Okay, so in the first couple of weeks, we have seen different feature engineering that you can apply in your data. You can extract motifs, work with orbits, work with standard topological properties of your graph. But what we're going to be seeing today is that how can we capture all of them together? Okay. All right. So let's go through an example. So this is basically what we want to do. So we want to have an efficient and task-independent feature learning for our machine learning with graphs. So First of all, we want it to be efficient, right? So we don't want to waste all the time that I was mentioning before to do the feature engineering. And at the same time, we want it to be task independent. So regardless of what's going to be your downstream task, ideally, we would like to have just one pipeline to do this automatic feature extraction, okay? So what we want here then is we take one random node from a graph, node U, and then we want to have a mapping function that goes from the node to an embedding, okay? And this embedding is will be in a d-dimensional space. We're going to be talking later on, how you choose the number of dimensions, but basically you can think of, in some way you're taking the representation of U in the graph and you're turning that into a vector representation, okay? And given the size of this vector, you will be able to squeeze there more or less information, right? But this is the kind of mapping that we want to perform. Now, why is it so useful? And where has this been applied? Okay. So now, say once we can do this mapping of each node in a low-dimensional space, then first of all, we obtain these distributed representations for the nodes that we can reuse in different tasks. And then, for example, if we have this vector representation, we can go and test what is the similarity between those embeddings, okay? And usually, if these vector representations are similar, we want that the nodes themselves are similar, okay? So they could be like adjacent in the graph, they could be connected, or they could have similar structural roles in the network. And at the end of the day, basically, we want that each node representation encodes as much network information as possible, all right? So basically, once again, this is the pipeline. We go from a large graph, then first of all, we can build our adjacency matrix, and this is the kind of representation that we don't like to work with directly because, as you remember, first of all, it tends to be very sparse, and at the same time is also very large. So it's very expensive to maintain as a data structure. So instead, what we want to do is that we want to have a more compact representation where now the columns are not anymore all the possible nodes in the graph, but rather are these what we call latent dimensions. So each of these dimensions will be able to capture some aspects of that node. Some of them maybe will be the motif it belongs to. Another column might be a mapping that tells us what is the degree of the node, and so forth. But the key point is that these dimensions are latent, okay? They're not explicit. We are not saying that each column is mapped to a specific feature, okay? Like each one of them will map to a certain subset of these features. Now, the kind of tasks that you can be working on once you obtain these distributed representations, we have a variety of them. They can be used to do anomaly detection. They can be used also to predict features, to predict attributes about nodes. They can definitely be used for clustering, link prediction, as we mentioned before, and so forth. So one of the reasons why when we talk about the projects, I often refer to this kind of techniques is because it's extremely powerful. So once you obtain this representation, then they can be used for a lot of different tasks, which I hope will be very useful for your projects. Now, let me give you an example that we already talked about during the community detection lecture. So if you remember, we were taking a look at this Zachary's Karate Club. So this is a club that split after the two owners had an argument, and basically this is the input, the standard graph representation, and if, say, we produce a two-dimensional embedding, this is what the output will look like, okay? So you see here the features, the axes are not labeled at all, okay? So we don't know exactly what this feature represents, but we just know that, similar nodes are gonna be close to each other, So like these communities that we identified in that graph on the left now will be mapped to nodes that are close to each other in our embedding space. And clearly, in the real world, we will not be using two-dimensional embeddings, okay? Usually we talk about hundreds of dimensions or sometimes even thousands of dimensions, okay? But for the sake of visualizing this is a very nice, given it's a toy example done already in a 2D representation, you can already distinguish nodes belonging to different communities, okay? So this is the kind of expectation that we have. Now, why is this problem hard? Why am I not referring you, to a course in, machine learning, on vision, or NLP? The reason is most of the modern deep learning toolbox is designed for very simple data structures, such as sequences or grids. So Let's start from vision, okay? You might have seen a lot of examples of how you can apply convolutional neural networks, and what you do in a CNN is that you take your convolutional window and you just pass it over the image, okay? And an image can be thought as a grid, okay? So this very regular lattice where each pixel represents a node, and this is far from what we actually see in a real-world graph, right? We never see this kind of regularity. So it's very hard to apply in a straightforward manner a CNN to a graph. Similarly, we could be borrowing on the work done in natural language processing. We know that recurrent neural networks work very well there, and also we have seen examples on how to extract embeddings with techniques such as word-to-vec or even more recent ones. What is the problem there? Usually the way in which we represent text is as a chain graph. Okay, so we have our tokens, we have our next token edge that connects them, and again, that's not something even remotely close to how a graph looks like in terms of complexity. So now let's think about the CNN example. If you think that the black nodes are those that are actually present in the graph, while the white one are just missing entries in our lattice, then you will see that once you have your convolutional window moving over this lattice, you will be taking into account nodes that are actually missing in this grid structure, okay? So this is not the right paradigm to work with on a graph. And the reason is, in graphs, you cannot establish a fixed node ordering, okay? Or you cannot find a single reference point as you will be doing, for instance, in text, where you have subject, objects, and so forth. And this is commonly referred to as the isomorphism problem. So you can take a graph, you can change holder labels, or you can even permute the columns or rows in an adjacency matrix, and the topological features of the resulting graph will be exactly the same, even if you shuffled all the labels. Okay, but while this is not the case, for example, with text. So that's why we need something much more powerful compared to the standard representational learning techniques, okay? And to make things even worse, and again, this applies to a lot of projects that I've been hearing in the past couple of weeks, graphs can also be dynamic. So you could have nodes appearing and disappearing, same with edges, and they can also have multimodal features, okay? So if anything, there are yet other reasons why we need more advanced tools for representational learning. Okay, so this was my intro, and now we're gonna be focusing on how we can embed nodes in graphs. Any questions? Or I can move forward. Okay, let's start with this. So very quickly, what is our setup? We have our graph G, V is our vertex set, A is the adjacency matrix. We're gonna be working with a binary adjacency matrix today, so no, let's not think about weights. We're just gonna be thinking about the connectivity between the nodes. And for now, we're not going to be thinking of any node features or extra information. We're going to be adding this additional layer of complexity starting from Thursday. Okay, so we're going to be talking about techniques that can also take into account the node features. But for today, we're going to be doing without them. So what does it mean to embed nodes? Okay, so our goal is to encode nodes in such a way that the similarity in our embedding space, so for instance, these are the vector representations of our node U and B. So if we take the dot product as a way to represent their similarity, this approximates well the similarity in the original network. Now, this sounds like it's basically a chicken and egg problem now. What is similarity? Okay, so one has to define what is similarity before they can come up with a proper mapping. So for example, if we consider similarity to be the fact that two nodes are connected, then we want adjacent nodes to be close in the embedding space. Conversely, if we care more, about the structural roles that nodes are having in a graph, we don't care that much if they're close in the embedding space when they're neighbors, but rather when they have the same structural role in a graph, okay? So the two definitions have to go, side by side. You need to first decide what kind of similarity you want to capture in your original network, and then after you can produce your encoding function. And the techniques that we're going to be seeing today will not only try to capture the adjacency, but rather we're going to also be seeing the structural roles, okay? So you will get a full overview. Okay, so this is basically what we were just saying. This is our goal. So we want to produce, given the similarity in the original network, one way to try to compute the similarity between the vectors is to take their dot products, or in case all the coordinates are positive, then it's basically the cosine of the angle between them. And so as I said, we need to first define this similarity, and then once we have done that, we can come up with our encoding function. So how do we now learn the full pipeline, okay? So as we said, first we want to define an encoder, okay? And an encoder is this object that maps from the nodes to the embedding space, okay? So from a node in the graph to a vector representation. Then we want to define our node similarity function, okay? So for instance, measure similarity in the regional network. And then at the end of the day, we are gonna want to optimize the parameters of our encoder in such a way that we're gonna get the best possible result for this equation, okay? So that the similarity in the regional network is as close as possible to the similarity of the embedding. So given the different techniques that we're gonna be seeing today, for each one of them, we're gonna explore how exactly the parameters are optimized. So how do we learn the optimal model? Question?
To measure the similarities, like cosine distance, or?
Yeah, exactly. So what I was mentioning before is here is represented as the dot product. It can be the cosine distance. We're going to be seeing, the cosine similarity. We're going to be seeing also there are different ways to aggregate this vector representation. So maybe you will want to sum them, or you want to get the average. So depending on your problem, you can come up with different similarity representations. But in the literature, this is the kind of similarity that is most used. So I would recommend you to start from there. Thanks. Question?
Do we care if two nodes have different similarities, but they're not very similar, that their embeddings still end up close to each other?
Oh, great question. So do we care if two nodes, even though they are not similar to each other in the original network, given our definition of similarity, they end up being close to each other in the embedding space? The answer is it depends on the model. So some models try also to optimize these aspects, so that they try to have as much distance as possible between the similar nodes. And we're going to be seeing a model today that exactly does that. So in the loss function, it will encode both the fact that similar nodes should be close to each other and the similar ones should be as far as possible. But it's all up to you on how you define your loss function. Thanks, good question. Anything else? Okay, let's move forward. So these are our key components. So we just said it, we need our encoder. And as I was mentioning before, we're going to be working with a d-dimensional embedding. And the number of dimensions is usually an hyperparameter that is up to the person who's training the model. Okay? So most of the papers that we're going to be seeing today, they either have some empirical proof of what is a good value for D, depending on the type of graph, or they usually come with default values. And most of the times, these values are reasonable enough, okay? So they tend to be in the order of hundreds of dimensions, okay? That usually captures a good balance between how computationally expensive it is to train the model, but at the same time, how expressive it's going to be, okay? All right, so now, as we recall, the two key components we're going to be working with are the encoder and the similarity function. So what are we going to do now? Let's start from the most simple model that you can think of, okay? So the first model that we're going to be talking about are just this class of shallow encoders. And the idea of shallow encoding is that an encoder is nothing but an embedding lookup, okay? So in computer science terms, an encoder is nothing but a hash table, okay? Given the node has a key, we're going to be returning a value which is a vector that represents the node, okay? So basically, we will have a matrix where each column is a node embedding. So this is what we want to learn. And then we're going to be having an indicator vector that has all zeros except a 1 in the column indicating our node V, okay? So this is basically how you build a hash table with matrices rather than how you usually do with a standard programming library, okay? So exactly the same concept. Now, how does this look like? So our embedding matrix will have basically one column per node, but then the number of rows will be exactly equal to the dimensionality of our embedding, okay? So each embedding vector will correspond to one of the nodes in our graph, okay? So this is the class of embeddings that we're going to be seeing today, basically. Once we train our model and we find what are the best values, the best coordinates for each vector to optimize our loss function, then these embeddings will be static, okay, in our downstream tasks. So we will have this fixed representation, and then we're going to be using it throughout our machine learning pipeline. What we're going to be seeing in the next lectures is that you can also work with contextual embeddings. So the fact that depending on which target node you're considering, then we will also be modifying what are the values of these vectors, but not for today, okay? So today, this is the kind of assumption that we're going to be using. Okay, so what are the methods that rely on these paradigms? So today we're going to be talking about deep work, first of all, then Node2Vec, which is an extension over the deep work paradigm, and then I'm going to also be giving you a real-world example applied on knowledge graph, which is called TransZ, okay? So translational embeddings. Okay, so let's go back to the problem that we were mentioning before. So how do we define our node similarity? These are some of the ideas that I was mentioning before. Two nodes should be similar in the embeddings if they are, for instance, connected. If they share neighbors, so for instance, you take their egonets and you find if they have a high intersection, so like if the Jacquard similarity of the egonet of two nodes is very high, or you might want to check what are the structural roles of the node, and many other things that you can also try to play with during your project. For example, you could think of two nodes should be similar to each other if they belong to the same community, or if you have some external domain knowledge about your graph that will tell you if two nodes share a feature, for example, okay? Or maybe they've been generated at the same time. So you can get as creative as you want on this part, okay? Any questions? Or we go through the random walk approaches. Okay, perfect. So as I said, these are the paper references that you can look at. So we're going to be talking about deep work from 2014 and then Node2Vec from 2016. Oh yeah, something I forgot to tell you at the beginning. Everything that we're going to be seeing today has been published in the time span of 5 to 6 years. So like I think the oldest papers that we're going to be seeing today is from 2013, okay? So these are very recent techniques. If you find problems about them, if you find even code implementations that are buggy online, don't be surprised. Like these are very cutting-edge technologies. So that's part of the fun that you will have in the project. Okay, so random walk approaches. First of all, what is a random walk? Okay, you might have seen it in other courses, but I couldn't resist the opportunity of using this very cool animation. So, okay, so we start from node 4, and then our explorer just works around the graph with a random strategy. And this specific case of random walk is called random walk with restart, because we're always restarting from the same node, okay? Or you could also have random walks that start from random nodes in your graph. So there's a very wide taxonomy of different random walks. But for what we care about today is that a random walk is, you're given a graph, you're given a starting point, in our case is node 4, and then what we do is we select a neighbor at random, okay? And we just move forward. Now, the random sequence of all the nodes that you're gonna be exploring is basically the random walk on the graph. And another parameter that you can be setting is how long your random walk should be, okay? Like in the case of the animation, you've seen that sometimes we explore 8 nodes, sometimes we explore 2 of them. You can also decide to have a bounded random walk, so always exploring no more than 5 nodes, okay? So each one of these choices in the upper parameters will come with a certain trade-off. And we're gonna be seeing in the different techniques that these random walks are used in slightly different ways. Okay, so why do we care about this? Why do we care about generating embeddings through random walks? The reason is what we want to capture. So remember, this is our expression for finding the similarity between the vector representation of 2 nodes. What it should actually capture is the probability that U and V are going to be co-occurring in a random walk over the network. Okay? So it's a very elegant and simple definition. Basically, if 2 embeddings are close to each other, then we expect that with a high probability of a random walk will traverse over them at the same time, okay? And depending now, you can already start to see the intuition. Depending on how we tweak our random walk, how we change the parameters of the random walk, this could be capturing different concepts. It could be capturing the fact that nodes are neighbors, or they are adjacent, or they have different structural roles, and so forth. Okay, so that's basically the core of what we're going to be seeing from now on in the lecture. Okay, so just this is a bit more a visual example. So once again, starting from node U, and then when we say that they have to co-occur in the same random walk, just keep in mind that it doesn't mean that after U, the first step should be directly B, okay? So they just have to be part of the same path that the random walk has been going through, okay? So once we set this initial probability estimation, what we do is we want to optimize our embeddings to encode these random walk statistics. So what we want to do is the fact that if they co-occur in the same random walk, then, for instance, the dot product, or the cosine of the angle of the two vectors representing those nodes has to be as close as possible to 1. Okay? So this is the idea of how we are going to go from the general shallow embedding framework that we talked about at the beginning on how to actually implement it with random walks. So why do we want to use random walks? Okay? Couple of key reasons. The first one is they're very expressive. So the example that I was mentioning before, given that they're very flexible in the way we can run them, we can both try to incorporate local information or higher order neighboring information depending on how we perform the random walk on the graph. At the same time, another reasons why we like to use random walks a lot is the fact that they're very efficient. So basically what they do is they avoid considering all the node pairs when training. And the only node that we'll be considering at training time are the pairs that are co-occurring in our random walk. And this part is extremely important. Like if you think about it, as soon as a graph starts to grow, if you have to work with all the pairwise comparisons to compute the similarity, that will suffer a quadratic explosion. Okay, so very quickly it will be computationally non-feasible to apply to obtain embeddings on our graph. So that's why we really like to use random walks, because they bring in this efficiency factor that allows us to scale to very large graphs. And when I'm talking about large graphs, just to give an idea, we're going to be seeing this already on Thursday, but I just wanted to give a spoiler. I'm talking about graphs with billions of nodes. Okay, so these techniques have been used successfully on real-world graphs, like real social networks. So extremely scalable. All right, so how do we perform our unsupervised feature learning? Okay, everything that we're going to be seeing today, contrary to what we talked about on Thursday, is going to be unsupervised. Okay, so we don't need any external labels. We are just going to go from the topological features of the graph to our embedding representation. Okay, so again, intuition. We're going to find the embeddings of nodes that are d-dimensional and that are preserving the similarity. What we want to do is that we want to learn these embeddings such that the nearby nodes are close together in the network. Now, given our node U, how do we define the nearby nodes? Okay, we don't have any more access now to the full graph, correct? We're just exploring the graph by means of random walk. So in some way, we need to redefine what is the neighborhood of a node, okay? So what we're going to be doing is that the neighborhood of a node is obtained by some strategy R, which means we're going to be deciding how many random walks do we run starting from our node U, what are the characteristics of the random walk, and so forth. Why is this important? Yeah, can you give me an intuition why we're not just going to blindly use the full neighborhood of every node? It's related to the efficiency argument I was making just one slide ago. Yeah.
If you have like a billion nodes, then your neighborhood could get very large if there are a lot of edges between all of them. So we only care about the ones that we got on the random.
Exactly, great. So if the degree of one of our nodes is extremely high, then we are losing basically our efficiency argument from here, because we will be performing 1 million pairwise comparisons just because the degree of the node is extremely high. And as we have seen since the beginning of the course, a lot of these networks follow a power law when it comes to the degree distribution. So you would be expecting a lot of those nodes to have very large neighborhoods, okay? So that's why we can't afford to just use all the neighborhoods, okay? So depending on technique we're gonna be seeing today, we're gonna find ways to restrict the scope, either by means of how many random walks we run, or it could just be also a fixed parameter, so you decide to randomly sample 20 neighbors for each one of your nodes, okay? All right, so let's start to formalize a bit more the problem, okay? So once again, we have our graph G. The goal is to learn our mapping. So from nodes, we're going to want to go to our d-dimensional embedding space. And then now we can express our objective as in terms of log likelihood. So what we're going to try to do is we're going to try to maximize this expression, which basically it's the conditional probability of, given the vector representation of our node U, what is the probability of finding the neighborhood that we defined before with our strategy R, okay? So we want to basically maximize how high is the probability that the vector representation of our node U is going to be close to the representation of the neighborhood, okay? And the reason why we express this in terms of log likelihood, we're going to be seeing again this till the end of the lecture, is because these are products between probabilities, right? So what happens is very quickly those values are going to become extremely small. And this leads to numerical instability when you try to optimize, okay? So that's why we turn basically everything into logs. So all the logs that you're going to be seeing from now on are coming from the log likelihood. You can pretty much ignore them in some sense, right? They don't help you at all in the intuition of how this works, okay? We just have to use them to make sure that we're going to be able to converge to the optimal solution. Okay, so now that we clarify this, basically the goal of our objective function is that it's going to help us to learn feature representation that are predictive of the nodes in its neighborhood, okay? So we get the feature representation of U, and then this feature representation is going to be predictive of what are the neighborhoods of that node, all right? Now, how do we turn this in practice? How do we make it work, okay? So for example, one way is we're going to start to run a lot of short fixed length random walks, which are starting from each node on the graph. And these random walks are going to be following our strategy R, okay? So the reason why we're talking about this strategy R is we're going to be seeing it in a while. You could either just run short fixed length random walks, or you can also, once again, try to be smarter there, try to add these random walks exploring the graph in different ways. So the initial technique that we talked about before, this is basically the description of deep walk that use unbiased random walks of fixed length. And later on, we're going to be seeing how having a more advanced strategy gives us even better node representation, okay? Now, what we do is for each node for where we are running our random walks, we collect the multi-sets of nodes visited on the random walk starting from U. The reason why this is a multi-set is because the random walk, especially if it's a first-order random walk, doesn't keep track of which node have already been visited. So you could basically be visiting multiple times the same node during a random walk, okay? So that's why instead of just being a set, this is a multi-set. Okay, and as we said before, then we're going to be optimizing our embeddings given our objective function. Now, how do we make this work for real? So how do we turn this problem into a abstract objective function into something that we can actually optimize? So that's how we're gonna be turning this. So we go from a maximization problem to something expressed as a loss, okay? So here, once again, we have our concept of given the representation of our node U in the embedding space, how well can it predict the node in the neighborhoods? And we're actually going to be doing this, okay, for B, which are all the nodes in the neighborhood of U, given our strategy R, okay? So this is the inner summation, the inner loop. And then we're also going to have to do this for each node in our graph, okay? So this is the vertex set of our graph, okay? So we're going to be doing this for each single node in our graph. And so once again, we're optimizing the embeddings to maximize that log likelihood, right? Now, how do we parameterize this in a way that we can actually compute it? So the idea is that we can use a softmax. You might have seen this in a lot of machine learning courses, but let me go through that once again. The idea is that we want our node B to be the most similar to node U, right? So what we do here is we take the similarity between the two vector representations, and what the softmax does for us is that it turns vectors into a probability distribution, okay? So these values, when we take the exponential of the dot product between these two vectors, what we will be getting are real values, and we want to turn these into a probability distribution. So it will tell us how likely it is that if we're starting from node U, the representation of node V is close to it, okay? And the sum of this denominator goes to 1, okay? And the intuition here is that if you take the exponent, if you sum over all the possible similarities between the nodes in your graph, this is almost equal to the entry of the highest similarity between the vectors. So say B is the node with the highest similarity with U. Basically, this is almost equal to ZU, ZV, okay? So between is almost equal to the dot product of these two vectors. So why do we want to use this? Okay, we need to turn this problem from this loss function expression into something that gives us the probability distribution among all the different similarities. Now, who can see an issue here in terms of efficiency? Yeah?
Summing over like all the vertices.
Exactly. Exactly. So, great. The problem here is that we are having, once again, a quadratic explosion, okay, which we always don't want with computers. So as computer scientists, we don't like anything that is above n log n, right? So here the problem is that we are iterating over all the nodes in the graph in this loop, and here we're basically finding all the similarities between all the nodes in the graph, okay? So we cannot afford running something that expensive. So now we're going to try to find a way to express this loss function that will not require us to have this double loop that has a quadratic cost over the number of nodes in the graph, okay? So this is basically what I was trying to tell you. This is the sum over all the nodes in our graph. So you see all over the vertex set. I'm coming to your question. And this is instead the inner loop, so the sum over all the nodes B that we are seeing during the random walk. Okay, so basically this is our concept of neighborhood given our R strategy. And this is the probability of U and V occurring in the random walk, which is expressed in terms of softmax. Okay, so ideally we could be using this for a small graph, but for the reason that we just mentioned, this expression will not allow us to scale to anything large. There was a question. Yeah.
So is the idea behind using this loss function to create embeddings such that if we do have random walks, if we do have random walks, the loss function will be at the minimum possible value?
Exactly, exactly. We're minimizing that. That's why we have a minus here. You can turn that into a maximization problem if you would like. Yes. Yeah, but again, the idea is exactly what you said. We're trying to find the embeddings such that similar nodes are close to each other, and similar in our case means nodes co-occurring in the same random walk, okay? So this loss function is capturing exactly that. Now, we need to go one step forward and remove the quadratic issue here, okay? So these nested sums are giving us complexity of vertex set to the power of 2. So the problem is we cannot really avoid this summation, right? I mean, we need to generate one embedding per node. So the fact that we're going to be doing that for each node in the graph is unavoidable. So where can we fix the problem? We're going to try to fix it from here, right? So we're going to try to avoid having all these similarity computations. So how can we approximate this? Luckily, we don't have to take into account each single node in the graph, okay? So how are we going to do this? The solution is negative sampling, which is something that has been used commonly before, so it hasn't been invented for representation learning on graphs. If you have taken 224N, deep learning for NLP, or if you have read the Word2Vec paper, so these are concepts that have been floating around since a few years. So the concept of negative sampling is the following, is that rather than trying to compute this similarity among all the nodes, we just take, you use a random distribution over all the nodes, and then we take a small sample of them, okay? And we're gonna call this our negative sample. So what we're gonna be doing is, we're gonna be using two nodes that we consider to be similar, and then we're gonna then be computing the similarity between random nodes in the graph, okay? And hopefully, the expectation is that the similarity with these random nodes will be much lower, okay? And keep in mind that this random distribution is over all the nodes, so sometimes in your negative sample, you might actually find the same node that is in your neighborhood, okay? It doesn't really affect the final outcome. Now, you might be also noticing another thing, in the way in which we express this new loss function. So first of all, we're using logarithm properties to make it more readable and easier to compute. We also moved away from the exponent, and we replaced that with a sigmoid function. So the sigmoid function is playing a similar role with what the softmax was doing for us. It's basically making sure that each term is gonna have a range between 0 and 1, so it's gonna be looking like a probability. Now, all the steps to go from here to here are slightly intricate, so what I've done for you is I put you a reference to a paper, and this paper actually explains how exactly the negative sampling in Word2Vec is done, and you will see that it applies straightforwardly also to this case, okay? So out of curiosity, basically, this technique is called noise contrastive estimation. The idea is that we are basically having a contrastive estimation, which means we are considering at the same time positive samples and negative samples, and we expect them to have very different similarity values. And the reason why it's noise is because this is an approximation. It's not going to give us the exact solution. But empirically, it has been found that it works extremely well. And it's much faster than what we have seen before with the accurate solution. Question?
Is that logarithm outside the summation, or like has that also shifted for some reason?
Oh, yeah. Go through this. That's the short answer. You will see how they bring it inside. But again, empirically, it doesn't make much difference. So yeah, but it makes things much easier to read for you, though. Any other questions? Okay. So the key takeaway from here is that instead of normalizing with regard to all the nodes in our graph, we're just normalizing against k random negative samples, okay? And this has been shown to work very well in practice, and it makes basically all our techniques from quadratic in cost to linear, all right? So it's a very desirable properties. Now, how do we perform our sampling, okay? And how many nodes are usually sampled by people? So usually what we do is that we sample k-negative nodes proportional to the degree. Now, we have two important considerations to make here. So on one end, the higher k gives a more robust estimates. The reason is we are taking nodes that are more representative in that graph, okay? If they're very much connected, it means that either they play a key structural role in the graph, or they're not outliers, they're not belonging not to, for instance, to no communities at all. At the same time, though, this is a trade-off, right? If we only use always the nodes with higher degree as our negative samples, we are basically biasing towards these negative events, okay? We're always using them as our negative samples. So this is in some way biasing the model. So in practice, what we do is we try to strike a good balance, and usually k ranges between 5 to 20 negative samples. But you never try to take always the top 10% of the node with the highest degree in your graph, okay? Otherwise, this will bias the value of your loss function. Okay, so let's put everything together. I know this was dense, but it's a pretty cool technique. So how do we do this now step by step? Let's take a high-level overview once again. So we're running our short fixed length random walks. We start from each node on the graph, and then we decide our strategy R on how this random walk should be traversing or exploring the graph. Then for each node U, we are collecting the multiset of the nodes visited in that random walk, okay? And then we're gonna be optimizing our embeddings, given our loss function. Clearly, this is a non-convex function, so we can use basically the same kind of tools that you have been using in all your other machine learning courses and projects. We're gonna be using stochastic gradient descent, okay? So we're gonna be trying to minimize the loss. And as we have seen before, going from this high-level definition of the loss function, we find a way to efficiently approximate it through negative sampling, okay? So we solved the efficiency problem, and we know for a fact that SGD can be made extremely efficient as well. So finding the minimum for this loss is relatively easy, apart from usually getting stuck in local minima, which is one of the standard problems of SGD, but we have good techniques on how to avoid that. Question from back there.
Yeah, can you go back to the previous slide real quick?
Here?
Would we see some benefit if we subtracted the average of that summation versus the summation directly?
Talking about this one?
Yeah, if we made that an average basically over all random nodes.
Okay, what do you think would be the benefit if we, instead of, so the subtraction, instead of this summation, we take the average?
Yeah, so maybe that would give you like a measure of the average similarity between this node and any given random node. I don't know, just out of curiosity, do you think that would give any benefit? Or?
Yeah, I think in general that might add some robustness in case the characteristics of the node you selected in your negative sample were very, very different. I think in the empirically it wouldn't make too much difference at the end of the day because these k nodes that we select tend to be quite similar. Okay, so like as we said, they're skewed towards the nodes with higher degree. So I don't expect them to be to make a big difference. But it's definitely something you can try to explore in a project. It would be a cool thing to check out.
And one more question. Sure. So I guess we're using random walks to gather a neighborhood of a given node. So why don't we just gather the neighborhood directly? Like, for example, if our graph is represented as an adjacency matrix, what is the benefit of using random walks if we're just directly gathering all the neighbors up to a certain depth?
Great. So the question is, why don't we work directly with a neighborhood? Why we go through this proxy of using a random walk to gather it? Two reasons. First one, as we said, is efficiency. If you work directly with a neighborhood, that might be very large. So you might be selecting nodes that have millions of neighbors, and then all of a sudden you're performing millions of pairwise comparisons. And the second one is working only with the one-hop neighborhood or two-hop neighborhood can be very restrictive in terms of what you're exploring in the graph. So what we're going to be seeing exactly in a bit is that we can bias these random walks, rather than exploring the breadth of the graph, we'll go in depth. And then in that case, we're going to be able to capture long-term dependencies between nodes. Okay, so that's why we use a random walk because it's a more flexible tool that you can parameterize and make it behave in every way you want. Thanks, great question.
Do you do anything to restrict the magnitude of these embeddings, or do you just let them kind of go wherever and let this loss function kind of just, if nodes are very similar, blow up in terms of...
Oh, no, yeah, great question. So do we do anything in order to bound the magnitude of these embedding vectors or not? The answer is yes. We are not going to see this in detail now. It's actually one of the questions that we have in the homework about Franzi. So we ask you what happens if you don't. Yeah. Actually, I kind of spoiled the answer because I think it was posed in the other way. But OK, so now you know that there is something related to the vector norm that makes a difference. But yeah, absolutely. Like you always have to take that into account because otherwise, one way to minimize the loss would be to have your vectors growing in size. And then even if the angle between them is not very close, the similarity will become very high just because the magnitude is similar. Yeah, great question.
In practice, is it possible to avoid actually simulating the random walks by taking the adjacency matrix and normalizing it for probability transition matrix and sampling probability.
Totally. Okay, great question. So the question is, can we simulate the random walks rather than actually running an actual random walk on the graph? The answer is yes. And the addendum is you always want to do what you're saying, at least most of the times. The reason is random walks, though, are very easy to implement. They're very taxing in your memory hierarchy. So the fact that you're going to be doing a lot of random accesses means that you will get a lot of misses in your cache, first level memory, and so forth. So there are ways to make them very efficient, but I wouldn't do that approach first of all. So there are ways basically to simulate them through the adjacency list or matrix. But yeah, from the logical standpoint, it's exactly the same thing. Yeah, great question.
Let's see the negative samples. So how do we ensure like they're far away from the node that we are considering? Like they're dissimilar from the nodes that we are.
We don't ensure that. So the question is, how do we ensure that the negative samples are far away from our target node view? So as I was saying, we actually don't ensure that. You could even be selecting a node vid which is actually part of the neighborhood of view. And it doesn't affect that much at the end of the day your loss function, because all the other nodes will be negative samples. So rather than trying to take into account the state of your random walk and do a smart negative sample selection, you try to do it in the cheapest possible way. Okay, and given that graphs tends to be very large, and we do this for each node in our graph, it doesn't affect that much at the end of the day the embeddings that you produce. Okay, thanks. Great question. Anyone else? Awesome. Okay. Hope this is clear, because basically it's the foundation of everything else that we're going to be seeing now. So this is exactly the intro of where I left before. So how shall we perform these random walks? So what we have seen up to now is deep walk. Okay, so it's the simplest possible idea, where we just run fixed length unbiased random walks starting from each node. Okay, and the issue is that here the notion of similarity is very much constrained. Okay, because these random walks pretty much all behave the same. There is this fixed length factor which doesn't allow you to go and explore other sides of the graph. So say if there are two nodes that have a similar structural role in the graph but they're very far away, you will never be able to capture the similarity, given that the length of your random walk is fixed. Okay, so how can we start from this framework, and how can we generalize it? How can we make it more expressive and more powerful? Okay, so what strategies can we employ to make that happen? Okay, so the goal is exactly the same. So we're going to try to solve exactly the same problem, and the kind of optimization problem also is the same. We're still looking for a maximum likelihood, and this optimization problem will be independent to the downstream prediction task. So we're working still with an unsupervised machine learning pipeline, and the key observation here is that we want to have a more flexible notion of neighborhood, okay, that will lead to an even richer and more expressive node embedding. And what we're going to be using to solve this problem is, rather than using standard random walks, we're going to be developing biased second-order random walks to generate our network neighborhood. So now we're going to be spending all our time on these two aspects of this sentence. What does it mean to have a biased random walk, and what does it mean that it's a second-order random walk? Okay, so no worries, I'm going to go in detail and make sure that you understand that. So this is the idea behind the paper called Node2Vec from 2016, coming from our group. And the key catch is that basically Node2Vec strikes a balance between the local and the global views of the network. Okay, so what we saw until before is only the local in deep walk. What Node2Vec brings to the picture is also that it will allow us to capture a global view over the graph. So how does this happen in reality? So as you know, you can traverse graphs with many different strategies. Possibly the CS101 versions that you have heard of for sure are the breadth first search, the BFS, and the depth first one. Okay, so if we only use a BFS, for example, starting from our node U, we get a very clear view over the neighborhood of U, but we're not able, to walk towards other sides of the graph, okay? So basically, the reason why the walks we're going to be using, we call them bias, is because we're going to try to find a trade-off between how much we perform a BFS and how much we perform instead a DFS, okay? So as simple as that. And so as an example, say, we decide that our walk will be on length 3. In the case of a BFS, for instance, starting from U, we will be exploring only nodes S1, S2, S3, and this is basically a microscopic U. We're just taking all the nodes around U. Instead, if we perform a DFS, so this is, now we replace our R in the strategy. Remember when we were calling this neighborhood of R? So now the strategy here is the way in which we traverse the graph, okay? So our strategy to get this neighborhood N is the DFS, and in this case, we're gonna be traversing through S4, S5, and S6, okay? And this gives us a global microscopic view over the graph, okay? So just these are the two main concepts that you have to keep in mind to understand everything else about Node2Vec from now on, okay? So the trade-off between BFS and DFS. Now, how do we actually encode this trade-off? It's pretty easy. There's just going to be two hyperparameters in the model. So apart from everything else that we've seen before regarding deep walk, we're going to be adding just these two parameters. One is the parameter P, which is a return parameter. It basically tells us what is the probability that we're going to be returning back to the previous node. So we just take a step back, okay? And then the parameter Q, which is what we call the in and out parameter, is the trade-off between moving outwards, so the DFS, versus inwards, so just performing a BFS, okay? And intuitively, what this Q parameter is capturing is the ratio between how often you perform a BFS versus how often you perform a DFS, okay? Any questions? Perfect, okay. So now what we said before is that we're developing biased and second order random walks, okay? So biased, we just explained it now, basically through these P and Q parameters. Now the reason why they're second order is because we're also keeping state, okay? So we're also having a random walk which is aware of the state that it took just one step before, all right? So say we are currently in node W and we came from node S1, what a second order random walk is able to do for us is to say, okay, the previous step was S1, and this is useful for us because basically for each transition among these different edges, it will be able to tell us if we're going back to our origin node or not, okay? So that's why it's called second order. Okay, now let's start to put probabilities on each edge so that you can understand exactly how the random walk is moving around, okay? So as we said, our walker, it came over edge from S1 to W and is currently in W, okay? So where can our walker go now from node W, okay? So we set our P and Q transition probabilities. We said P is our return parameter, Q is our walk away parameter. So we're going to say with probability 1 divided by P, our walker will go back to S1. Then with probability 1, and keep in mind that they are unnormalized, so we're going to normalize them at the end and make sure that they sum to 1, no worries. With probability 1, then our walker can go to S2, so basically it's performing a BFS. And then with probabilities 1 divided by Q, it will go out, okay? It will walk away and it will start to perform a DFS, so we'll start to explore nodes away in the graph, okay? So these are our transition probabilities. And that's how they're gonna look like, okay? So basically at each step, our random walk will keep on updating the transition probabilities, and we'll also keep the state in S1, okay? And in this way, we're basically performing a biased walk because, rather than as a standard random walk jumping on a different node with exactly uniform probability, now we'll be biased by the parameters that we decide to use for P and Q, okay? And for instance, nothing prevents you to give an extremely high value to P and make sure that the random walk never goes back, or you can make sure that you can give an extremely small value to Q, and then you're biasing the random walk in such a way that it always tries to explore and perform a DFS in the graph, okay? So this is basically what we were mentioning at the beginning, that given the kind of similarity function that you're trying to capture with your embeddings, then you need to train the right model and you need to find the right hyperparameters to make sure that it matches that original similarity function that you had in mind, okay? And in the paper, you can also find some empirical results on how different values of P and Q are able to capture different characteristics of a graph. Question?
So why are we treating the case of going from W to S2 similar to going from W to S3 or S4? Is it just because this is from S1?
Yes, so here basically these are all at distance 1 from S1, right? So in a sense you're saying if I move to S2, it's like if I'm performing a BFS of S1 from S1. I'm trying to explore all the neighbors of S1, okay? Instead here, if you move outside, then you start performing a DFS basically. Make sense? And the reason why you have only one parameter is because you can, given that these are normalized probabilities, you can always set the BFS edges to 1 and then express the other one as a ratio. So you don't need two parameters in that case. Thanks, great question. Anything else? Okay. Okay, we have to go fast because we have 20 minutes left. Okay, so let's recap very quickly our node-to-back algorithm. We compute our random walk probabilities. It's exactly the same of what I've seen before, even with deep walk. And then we're going to be simulating our random walks of length r starting from each node u. And here the key catch is the way in which we compute and perform these random walks is going to be depending on our P and Q parameters and the fact that we're biasing them more towards BFS or DFS. And then everything else is exactly as before, so we're going to be optimizing the same objective function and through stochastic gradient descent. The two good news in terms of efficiency are the following. First of all, this is still linear time in terms of complexity because we just changed slightly the behavior of the random walk, but everything else in terms of the optimization problem is exactly the same. And also these three steps can be parallelized individually, okay? So one can come up with a very fast implementation node to back. Any questions, or shall we jump to the next example? Okay, so let's quickly talk about how we can use the embeddings, and then I'm going to give you a real-world example on how we actually use them in knowledge graphs. So we talk about now how to do our representation learning of graphs, right? And we have these very cool and powerful vectors representing each node. What do we do with them, okay? So these are just numbers still. So first thing is we can use them to do clustering or community detection, right? So we can find a set of points in our embedding space that are close to each other, and then we can consider them to belong to the same community, if they are all within a certain radius. Or we can use this, for instance, to do node classification. So say we have a few labels, as as the second slide from today, and we have our node representation. So what we can train is our function f, which will be any classifier, an SVM, a decision tree, whatever you like. And then we train that to give us labels for each node in the graph. So as you can see now, we already solved the node classification that we talked about on Thursday with training a simple classifier over these vectors. Now we can also do link prediction, right? As I promised to you at the beginning. So that's how we do it. How do we predict hedges between two nodes I and j? So basically, even here, we can train a classifier. We're just going to be using the vector representation. The only difference is that now we're working with pairs of nodes, right? So we have to find a way on how to treat those two vectors in a smart way. There are a lot of different aggregation functions that you can explore. The simplest one is you can just concatenate those two vectors and then train your classifier over the concatenation of the vector representation. You can use a lot of different distances. You can even use the Euclidean distance, so the L2. You can sum them. You can average. depending on the characteristic of the graph, sometimes these aggregation functions, they all perform the same. Sometimes you will find very different accuracies, okay? So I always invite you to at least try the basic ones and see what kind of values you obtain, okay? Because it can be very tricky. Okay, so that's how you perform link prediction, and if you go through the papers that we're going to be posting online, you can also see other example of standard predictive tasks you can do on graphs based on these embeddings. Okay, so what we covered today is basically random walk approaches to define node similarity, and basically we moved away from the concept of, let's say, only using the adjacency-based features or multi-op similarity, so how much they have in common in terms of neighborhood, to something more powerful where we explore much more in depth our graph. So in terms of methods that you can use, I'm pointing you to this very interesting survey, and as I was mentioning before, none of these techniques is a silver bullet. None of them works on each single graph and on each single task in a great way. So for instance, in this survey, they found out that Node2Vec was great when it came to node classification, but then there are better methods for link prediction. So if you want to use any of these techniques for your project, go through this survey, ask us, ask me or the TAs, and then we can try to point you to what we know works best in your use case, okay? But always have a critical point of view over these techniques rather than just applying them blindly, okay? Now, let's go to an example applied over knowledge graphs, okay? So this is a paper called Translating Embeddings for Modeling Multi-Relational Data. So very advanced title. It's a NURIS paper from 2013. I'm going to try to make it very simple, give you the intuition, and then you will be working through this technique from a conceptual level during homework 2, okay? So what is a knowledge graph, first of all, okay? So a knowledge graph is composed of facts and statements about interrelated entities. For instance, this is a small snapshot about writers. So you have J.K. Rowling and you have Stephen King, and you see that they have some genre in common, like they've both written fantasy books, or Stephen King wrote science fiction books. And why are knowledge graphs interesting, and why aren't they just plain old graphs, okay? The reason is, in knowledge graphs, edges can be of many types. Okay, so we don't have only one edge, or we don't have edge weights, but we rather have types. Okay, so you see here the blue edges is influenced by, so like if a writer is influenced by another writer, or the green edges are the genre that the writer is using in their books, and you can have plenty more. Okay. Now, to make sure that you understand the jargon, if you go and read any of these papers, keep in mind that the nodes in these graphs are usually referred to as entities, and the edges of these graphs are usually referred to as relations or relationships, okay? So just keep in mind this mapping in your mind. What is a very important task that we usually perform on knowledge graphs? That task is completion. The reason is building these graphs is extremely expensive and tedious. So like if you think about a very big part of the effort in Google is to actually have a very accurate and vast knowledge graph that is able to encode a lot of information and relationship between entities. But it's very hard to have a complete overview, okay? So a lot of the relationship will be missing. For example, we would like to have an edge that says that J.K. Rowling has also written books in the science fiction genre. Why is this an important task? As I was mentioning, when one of these graphs is incomplete, it can really affect the efficiency of a system relying on it, okay? So if you're using this for a search system, the fact that one of those edges is missing might impact negatively the quality of the search results, okay? So that's why you want to try to complete those knowledge graphs. And the way in which we perform this completion is the same task that we talked about a while ago, right? This is link prediction, okay? It's just that in the context of knowledge graphs, we call it completion, okay? So what we want is, our downstream task is, we want to be able to predict if there are missing relationships between entities of similar type, and we want to also make sure that we're able to find what is the correct relation, okay? So not just the fact that there is an edge, but it's important to find the right type of that edge. So let's go through an animation. So this is the technique. It's called TransZ because it's a translating embedding. I will try to run around. So we start from our knowledge, so a small snapshot of the knowledge graph. we project it on our embedding space, and then at each step, what will happen here is we know that these two entities should be close together, right? Because they are influenced by each other. So at each step of the optimization, these two nodes are getting close to each other, and the reason is, we're going to go back there soon. So the reason is these edges, the general edges are both pointing to the fantasy entity node, right? So what this translating embedding does for us is that it tells us, okay, a relation is nothing but a translation in the space from an entity node, so the head entity node, to the tail entity node. So if those two nodes have 2 points, so if J.K. Rowling and C.S. Lewis have to point to the same tail entity, then they have to get closer to each other in our embedding space, okay? So TransZ basically goes from this intuition to an objective function that optimizes the distance between these embeddings. Now, let's move away from the animation and let's try to see it as an example. So we formalize it in the following way. In TransZ, we call relationships between entities that are represented as triplets. So we have our head entity, which we call H. L is the relation, T is the tail entity. So all the information in TransZ is represented by these triplets, okay? And the first step in TransZ is we take our entities and we embed them in an entity space of dimensionality k, okay? And this is similar to all the previous methods that we've seen today. You can use any way you like to do this embedding. And then the key difference is that these relations are represented as translations. So as we said, we go from this entity space, and once we have our mapping of the entities, what we get is when we apply a relation, we are just basically translating or moving from one node to another. And the expectation is if this relation holds, then we should be finding a tail entity at the other side of the relation. If this relation doesn't hold, we expect here to be empty. Okay, we don't expect there to be any close by entity. Okay, so this is the kind of objective function that we are going to try to that we optimize for when we train our TransZ model. So how do we do this? Let's go quickly through the steps of the algorithm. So we start from a uniform initialization. So in this case, we're not even using random walks. Okay, it's an even relatively easier approach when it comes to produce the embedding vectors. These are our relations L. So we have a uniform initialization for all of them. We also normalize the length of the vector, and we do exactly the same thing for the entities, okay? So entities and relations are initialized uniformly, normalized, and they're all together in the embedding space right now. Now, what we do is, here we perform mini batching. Not important, you just have to keep in mind that we are not working with one triplet at a time, but we're working with a batch of triplets at a time. And what we do is, for every triplet that actually exists in our knowledge graph, so like this is a valid triplet, okay, head, relation, and entity, we also sample a corrupted triplet. And in terms of what we were talking about before, a corrupted triplet is not about negative sampling. So we try to get a triplet that doesn't exist. So we basically either replace the head or the tail with another random entity in our knowledge graph, okay? And the way in which then we're going to be updating our embedding, so this is similar to the optimization function we have seen before, for example, Node2Vec, is that we give weight to a positive sample. So we want to make sure that the distance between our head entity translated through our relation to T is as small as possible, because this is a valid triplet. And then we're going to be using our corrupted triplet as a negative sample, and what we want here is that this distance has to grow, right? Because we want that when we translate H prime with our relation L, it should be pointing to a very distant entity. So this value will grow, okay? And this is what's called a comparative loss. Basically what it does is it favors lower distance values for the valid triplets, and it instead gives high distance values for the corrupted ones, okay? So these are basically you go through multiple iterations of these until it converges, so the results become stable, and that's exactly what we were seeing in the animation, right? So we went from two head entities that were far from each other, and then we made them closer and closer because they were connected by a valid relation. Okay, so this is the whole intuition behind TransZ, And the reason why I wanted to show you this is, first of all, because using random walks is not the only way to generate embeddings, and at the same time, because this is also a very exciting type of graph where you can apply embedding techniques, okay? So knowledge graphs, if you're planning to use them also in your project, they're very cool data sets to work with, and you can answer a lot of cool questions on them. Any questions?
So are you just finding like commutative paths essentially? You're saying like there was a path to this, you know, it's chosen randomly to begin with. This might be multiple ways in this entangled relational graph.
Oh yeah, absolutely, yeah. You won't necessarily always end up in the same configuration, and given the fact that this negative sample is random, it will affect how you generate these valid paths and the invalid ones. But what you care at the end of the day, you don't care about the actual values of the vectors. You just care about the fact that some of these translations will be valid and some of them will be not valid.
And just to clarify, so if you found a path to like connecting two nodes, then you're saying there should also be an edge between those two nodes specifically. Or is that not correct?
Yeah, no. So this is up to how you train the model, how you learn it. And then, for instance, if you want to do knowledge graph completion, what you will be doing is you take a valid head entity, you apply a relation, and then you find that if after the translation that points or is very close to an entity that is actually present in your knowledge graph, then you say with high likelihood there should be an edge connecting the two of them. And that's how you perform the completion task. Okay? Great. Other questions? Okay, I will spend the last 2 minutes just telling you about embedding entire graphs. I'm just going to give you the intuition. There are more slides in here so that if you're curious, you can check how they work. But basically, the idea is that before we have seen a lot of different techniques on how you can embed nodes, in reality, you can also want maybe to embed an entire graph, okay? So you want to go from the original network to a single vector representation for the whole graph. Why would you want to do that? For example, it has been used to classify toxic versus non-toxic molecules. You can try to identify like anomalous graphs. Let's say you have a transaction graph in your bank system. Then with a single embedding, you can find out if that transaction is valid or not, and so forth. Okay, so these are the kind of tasks called graph classification tasks. 3 simple approaches. The first one is you just run a standard graph embedding technique on your graph. So let's say we do deep work, and then you just sum or average node embeddings in the subgraph, okay? So this is the simplest possible aggregation you can come up with. You sum all the vectors together, and that just gives you like a fingerprint that represents your graph. And for instance, this technique has been used a few years ago successfully to classify molecules based on their graph structure, okay? So pointer is there if you're curious. Again, a nice reference for your project. Another slightly more advanced approach is you can introduce a virtual node, so you can connect all together nodes in all the graph, or maybe even a subgraph of interest that you want to represent, and then you embed only that virtual node, okay? And again, this has been used as a general technique for subgraph embedding. I invite you to check the paper as well. Last idea, and you will find the slides here in case you want to go deeper and understand more, is the concept of anonymous walk embeddings. Basically, what they do is, you're in your graph, you're running your random walks, and rather than keeping track of all the nodes that you're visiting, you're just going to keep track if you're in which order you are visiting that node, okay? So say, you're going from A to B to C and to B again. The way in which you translate this random walk in a more compact representation is the fact that, okay, I've seen this node at step 1, I've seen B at step 2, I've seen C at step 3, but now that you go back to B, that's how you represent it in your random walk. You will say, okay, I visited this at step 2. And in some sense, what this captures is how often your random walk is going to be stuck in a neighborhood, or often is going to be visiting exactly the same nodes, okay? So now when you put all these representations from anonymous walks together, then once again you will be getting a more powerful fingerprint about your graph compared, for instance, to this one, okay? So there are a lot of slides here in case you're curious to check how exactly it works. So I'm running out of time if there are any questions, otherwise I'm happy to talk offline. Thank you.